Geologists can map rocks from space. So, geologists usually make geologic maps by visiting places and seeing what types of rocks are there and by mapping the locations of those rocks. But some areas are just so remote or rugged that we can't get to them. And one of those places is in the northwestern Himalaya. This area is not only geologically interesting, it includes some of Earth's most rugged topography and tallest mountains, like the second tallest mountain in the world, K2. So, when geologists can't walk directly to rocks, they can use other methods like satellites and gathering data from satellites. NASA's Terra satellite has an instrument called, are you ready? The Advanced Spaceborne Thermal Emission and Reflection Radiometer, or ASTER for short. This instrument gives scientists information about a type of light that humans can't see called thermal infrared. Now, when most people hear thermal infrared, they probably think about predator, or maybe they imagine cameras that show something warm, like a person or an animal. But what the camera is really detecting is light with wavelengths that are longer than that of visible light, which is the light that humans can see. Now, thermal infrared light is emitted or released by all objects, you, me, your cat, a tree. We can figure out what objects are by looking at how much thermal infrared light they emit at various wavelengths within that thermal infrared region of the electromagnetic spectrum. This is called their spectral signature, and it's like a fingerprint made of light. Now, every mineral has a unique spectral signature, and because rocks are made of different combinations of minerals, looking at all the fingerprints together reveals the rock type. So rather than looking at spectral signatures themselves over the whole area we wanted to map in the Himalayas, we use various colors to indicate rocks that have the same fingerprints and thus are likely to be the same type of rock. Now, geologic maps created with this thermal infrared data need to be checked to make sure that the rock type we put on our map made with satellite data matches the rock type that's really on the ground. Like, we got to do a reality check. So, to do this, we collected different types of rocks from the limited areas that we could visit within the area we wanted to map. Then we went back to the laboratory and used an instrument called a thermal emission spectrometer to measure the spectral signature of each rock. Now, when we compared these laboratory fingerprints to those from the satellite, they matched. So this gave us confidence that our geologic map was correct. Now, our map revealed some really interesting pieces of the Himalayan geologic puzzle. First, we could see remnants of an ancient ocean called the Tethys Sea that once separated India and Eurasia. About 50 million years ago, these two continents collided, pushing up the seafloor and beginning the long process of making the mountains that we see today, the Himalayan mountains. Our map also helped us to see the intersection of two huge faults, the Karakoram and Longmu faults, and these form the southwestern edge of the Tibetan Plateau. These faults are active today and could potentially host strong earthquakes. And so our geologic map helped to show which parts of the Karakoram fault might be most likely to have these earthquakes, which is really important information for people who live in the area and need to stay safe from these types of earthquakes. So to read more about this work, check out our open source scientific paper, Structural Relationship Between the Karakoram and Longmu fault Systems, Southwestern Tibetan Plateau, revealed by ASTER Remote Sensing.